Created this. So you guys know you guys might be my last class.
What? What happened?
What do you mean?
It's okay.
They have two classes
Uh-huh.
this next semester,
Uh-huh.
and I don't have any.
Really?
Yeah, and I asked them, and I haven't got any responses. And the only thing that kind of upset me is that I have to change things at Long Beach,
Uh-huh.
and I declined one. And I said, no, I can't.
Oh no, that's bad. They should
I
have.
don't know what happened, but I think the lecture class are asking because some of them want to be in this lab,
Yeah.
so everybody's gonna be asking next week. I don't know.
Well,
I
hope
don't
it
know.
works out.
Yeah, I'm gonna miss it. Anyways, it's all right. So motor parameters. So basically, the end goal is to come up with this circuit right here, so that you can use it. And we're gonna use those values on MATLAB Simulink. When you do not have them, right? Like if you're not to have them, but you have the motor here, and when you want to estimate that information, basically that's what we did. Lab number 9 and 10, both really. That's what we did. So the goal once again is to get the equivalent certain parameters from lab testing. And we say this is as seen from the stator. You guys remember when we were doing transformer with some of you probably, and we had a transformer, and it looked like this. And this is R1, this is JX1, this is R2, this is JX2. This is N1, this is N2, and this we call that the turns ratio, which is A, which was N1 over N2, right? And one thing that I discussed on the lecture on transformers is in order to get these parameters from the secondary, this is in the secondary, this is the primary, we can translate these impedances to the primary side of the transformer by multiplying, and the way that comes up is like this. Let's see it this way so that makes sense. This is a reactance and this. Right, so we end up with a circuit that looks like that. R1, JX1, JX, oh, I'm sorry, this should be
R2.
R. This is R2 prime, this is JX1, and this is JX2 prime. JX2 prime is really, R2 prime is equal to A squared times R2, and JX2 prime is A squared times JX2, right? So basically what I'm doing is I'm transferring all of the impedance so that it's being seen from the primary side of the transformer. Similarly for a generator or I'm seeing a motor, all I'm doing is I'm taking, with this circuit right here, I'm taking all the parameters from the rotor side, which in this case we can think of that as the secondary of a transformer, to the stator side. So this is already being transferred to the rotor side. So that's what I said, I seen from the stator side of the generator. The measure of the stator resistance, remember that we went over there, we actually measured, you guys took the measurement, and it says divide by 2 because you were taking the resistance of the two windings together, and then you guys remember that? And you have it on the notes. But this, basically, the stator resistance is really just straight measurement, right, that you do. Now, so that's the simple piece right here. In order to get the rest of the parameters of the generator, the magnetizing branch and the X's and the R2, then we have to perform the test. So there's two tests, and the first one we're going to talk about is the lag rotor test. So the lag rotor test is when S or the slip of the motor is equal to 1. What does that mean? You put a big load on it, right? So the slip of a motor is the speed, synchronous speed minus the actual speed divided by the synchronous speed. That speed right here is the speed of the magnetic field, of the field that you generate inside from the three phases, right? Now, when the motor obviously the motor is not running, this is zero, so 1800s, which is what we took this machine to, right? 1800 with no motor, and 1800 is equal to 1. So the slip's equal to 1. So when somebody tells you that the machine is not moving, meaning the rotor, you apply voltage and everything, but the rotor is not moving, it stands still. That's when the slip is equal to 1. So slip of 1 tells you the machine is at standstill, right? In our case, we have an 1800 RPM machines, they're 4-pole machines, right? So that's what we keep on trying to bring the machines at that speed. So the lag rotor, and I said, so we basically what we keep is a very large load on the shaft of the machine just to stop the machine. In some cases, you guys remember that the rotor was it was kind of moving, right? But not enough speed to make a big change on the result, right? Ideally, you have a load that is large enough that it will not allow the rotor to move. In a couple of cases, I thought, you know what, maybe we just put a screwdriver and hold it, but then I thought, you know what, I wouldn't want to hurt. So if you got close numbers, good enough, right? So what does that give you? The lag rotor state of the machine, it gives you this branch right here. So the current goes through this branch over here. So now you know the current, there is a way to measure this parameter based on the real power, the voltage, and the current measurements, right? Let me go to the next slide. Okay, so this is the circuit basically that we came up with, right? So this IV is the I current, is the current that goes here, and that's the branch that I told you, where there is the R1, R2, JX1, and JX2. So that rotor test gives the equivalent impedances of the stator and the rotor winding, okay? So ZE is basically this right here, ZE, and ZE is equal to the resistance plus the reactance combined, okay? So that's this equation right here. So the parameters we calculate measuring the stator three-phase power, line voltage, and line-to-line current. In our cases, we were measuring just a single phase power, right? Because we're just measuring one phase, but we can always use multiply by 3 to obtain the total, because each branch or each each phase carries the same amount of power, assuming that all 3 phases are balanced, which they should be, right? So with that information, what if you get this measurement? We got this voltage from the meter, we got this current from the meter, and then we also got this power from the meter. For this one is in this equation right here, this is a phase to neutral voltage that we need to use, okay? Not the phase to phase. So you got two, right? Remember you have the phase to phase and the phase to neutral voltages when we were doing the lab. So basically RE is equal to R1 plus R2. Remember, RE is equal to R1 plus R2. So what about X? Well, we can measure Z, but we cannot measure X. So the way we do it is X is really is ZE squared minus RE squared. That gives you the value of X total reactance of the machine, winding for the stator and winding for the rotor, right? Here's a table, and this is a standard table. There's different type of motors, and this is a NEMA. This comes from the national
electrical measurement standard, something like that. Is a standard that comes up with that provides with this value. So for motors, we have type A, B, C, and D. I think ours right here, our C, will verify that, but I'm pretty sure they are. So what it tells you is if you know X1, somehow if you know X1, I'm sorry, if you know X2, you can compute X1 by using these equations, right? So if you have a motor type C, which is defined by NEMA, type C, X1 is equal to 0.43 of X2, okay? And in this case, the current that we're gonna push through the motor is the rated current. So we're gonna try, remember we're trying to get we're trying to push the voltage until we get some amperage, and there was an option I can remember it might have been 2.3 something, I vaguely remember, but we'll go back to that. But the voltage, remember, you didn't have to get the voltage all the way to 208, but somewhere between, right? Remember we said keep on pushing the voltage, but do not exceed this current. You remember that? That's basically what we're trying to do. So when you're doing the lag rotor test, basically all you're looking for as far as measurement is the current to get to the rated value. And then the voltage, you do not want the voltage to be rated voltage because then this current will be very large. The current that goes through this will be very large and you can damage the windings, right? So you control the voltage here, but it doesn't really matter because that's going to give you V equals IR, right? That's what we're trying to do. All right, so that's the lag rotor test. The lag rotor test gives you the resistance and reactance of the stator and the rotor windings. Then the next one is the no load test. The no load test is when S or the slip is equal to 0. What does that mean? In that case, remember we completely unloaded the machine, right? We said, boom, we're not gonna put any load on the machine. So the machine was almost to 1800 RPMs. Ideally, we'll get it to 1800 RPMs. So in that case, the synchronous speed of the field, the rotational field speed, and the actual speed of the rotor are the same. In this case, 1800 by A, you get 0. So when the machine is, once again, at a synchronous speed, the slip of it is 0. I mentioned this in the last lecture, Maria, you remember when I said, for testing purposes, that's fine. But in real life, once you have the motor doing the work that you need the motor to do, you never want to run the motor at synchronous speed. Because induction machines are asynchronous, right? For them to do the work, you have to slow them down, or they have to run on there or behind its synchronous speed or the speed of the field, or rotational field, right? So when I said, as long as you keep that slip between less than 5%, meaning really close to synchronous but not synchronous, the machine should work, and that's your ideal condition, right? So that's what you want to achieve in real life. But for testing purposes, we want to bring it to that. So on that one, we measure voltage again, we measure current, and we measure power, right? So PEXC, VEXC, and IEXC. In this case, what we're after is the reactance or the excitation branch of the machine. Okay, this account for the core losses, rotational losses, and all that. So in this case, you want voltage to be rated. Now, in this case, you're going to crank up the voltage. In this, your case was all the way to 2A. The current, you want to keep the current between 25 and 40% of its rated, right, value. So how do we get the ZM? ZM is equal to Rm prime. The prime means that, hey, whatever we're doing it as seen from the stator side, okay? So Rm and Rm prime. So this is Zm is equal to the voltage that you measure, or what we call the excitation voltage, divided by the excitation current. The resistance is the power, the excitation power, divided by the excitation current squared, okay? Then you go through the same exercise. Oh, well, I do not know what well, I don't know how to measure XM. I don't know. I know how to do this. I know how to do that. But if I have this values, I can use this equation, right, to measure the RM and the RM and the XM. So, and last but not least, your RM is 2/3 of your RM prime. Let me do a quick example, and you already did this. So this is, you're gonna follow these equations, and this is basically what you got on your lab. This is just a different measurements, right? So if I have a 100 kilowatt, three-phase, 60 hertz, 480 volts, line to line, Y connected, which is your case, right? Machine that runs at 11.46 revolutions per minute. This machine, but by the way,
1200.
this 1200. This is a 1200 RPM machine, meaning the magnetic field or the rotational field that you create is going at 1200
Revolution per minute.
revolutions per minute. Okay, so they're telling us that this is a C-class machine. Oh, it's a C-class machine. So this is the equation we're going to be using shortly, and the results are the following. So the no-load test gave voltage 480, line to line, rated voltage. Power that you measured was 1,920 watts, and the excitation of the current that you measured was 40 amps, okay? For the lag rotor test, for this specific motor, we brought the voltage to 32 volts, right? So not rated, but somewhere between, right? And that gives us 2,560 watts. And it gives us a current, which is the rated current of the machine, of 65.6 amps, right? So now we have this information. Now we go through plugging in through the equation. So Rm is equal to the power times the current squared. And the reason why the 3 is because this is three-phase power. So I need to divide it by 3. Do I make sense? In our case, that's what we did. We don't have to divide it by 3. Why? Because we were just measuring the power
One.
in one phase, right? But in this test that they did, they measured the three-phase power, so that's what they divided by 3. Now, so that the Rm becomes 0.4 ohms per phase. That's the Rm prime, I'm sorry. The Rm of the machine is 2/3 of the Rm prime, so 2/3 of 0.4 is 0.27. Okay, R1, they didn't say here, but R1 is equal to 0.2, right? You guys did this too, right? Remember when you did this and it looked like this? And it had this, and I asked you to measure the resistance and divide it by 2? That's basically the value that they have on this test. So R1 is 0.2 divided by 1, that's 0.1 ohms, right? Okay, so that gives you the so this one is, remember, this is measured using meter. This is not computed from your test results. The R rotational, these are the losses. So how do you compute the rotational losses? It's Rm, which is excitation branch, minus R1 minus Rm. So Rm prime minus R1 minus Rm. So rotational losses in our case, with 0.4 minus 0.1 minus 0.27, 0.4, 0.27, 0.1, gives us the rotational losses of this machine at 0.033 ohms per phase. So this, remember, oh no, that was on the lecture, Maria, when I did that chart, where you have all the losses and then you have the rotational losses, that's what that number is. The other one are winding losses. Sorry, I have to go to the other one. So that's the one. Then the last part, I'm gonna go here. Sorry, I didn't want to erase and rewrite. The last part, it was the ZM of the machine. Okay, so how do I get ZM? The voltage, the excitation voltage divided by the excitation current. In this case, the voltage that they measure, they measure with the line-to-line voltage, right? But for this equation, I need line to neutral voltage, so I just divide it by square root of 3. right? To get the line to neutral voltage, divided by 40, which was the answer we got, that gives us 6.92 ohms per phase. Okay, so now we have x prime. If you want to find x prime, we cannot do it by the test. But we do know this value, we know this value, so we just plug it into the equation. So 6.92 squared minus 0.4 squared gives us an XM of 6.91 ohms per phase, okay? Remember, per phase. And then the lap rotor, that's lap phase. ZE is just the voltage. Remember, this is not rated voltage, but 8% of the rated voltage divided by 3, because still the value that they measure was line-to-line voltage. If you use the line-to-neutral voltage that you got, you don't have to divide it by square root of 3, right? So just think of that. And then the current that was measured was 65.6 amps, more or less. So RE is the power divided by the current squared. Power they measured was 22,560 watts divided by, you gotta remember the 3, because this measurement right here is 3-phase power. But for this formula, we need a single phase power. So divided by 3 times the current squared, that gives us an RE of 0.2 ohms per phase. R2 is equal to RE minus R1. Okay, so I know RE. I know R1 because I measured that with the meter, right? So R2 is equal to 0.2 minus 0.1 gives me 0.1 ohms, okay, per phase. Now the reactance. First we got the total reactance of the machine, which is the combination of the reactance of the stator and the rotor, okay? So on that one, we know that XE, we've had this value already, we got this value, so we compute this value, XE, which is the total combination. I know the value of XE, right? And I'm after this value, X1. Okay, so I need to solve for X1. I know that X2 is X2, remember that equation from the table, is equal to 0. Blah, blah, right? So, I need to solve for this X2, so I need to then solve for X2, which gives me X1 of 0.43, that's X2 plus X1. I know this value, 0.2, I solve for X1, make sense? And then I know that if I solve for that, that's 0.06 ohms per phase, and X2 is equal to 0.14 ohms per phase. Now I have and this is R, C, and X, M. Now I have values that I can enter into my computer model, or if I'm doing it by hand, right? So that's basically what we did. There's one little thing here. These numbers are all, and I'll talk to you guys when we're doing the simulation. The reason why they're off is because when you're doing the measurements, the frequency, the inside frequency on the rotor is 1/4 of the actual frequency. So, but how do you do that? On a real test, you cannot excite, right, the rotor at 15. We don't have the ability to change the frequency of the sources. So there is a factor to correct that, right? To do that, basically you divide by 4 and you assume that I was running at 15 hertz. On the simulation, you can do it because you can change the frequency of the source, right? But not here. So we'll do that. Okay, so what I'm gonna do, let me go through this whole thing with the other groups, and then we'll go upstairs and I'll show you how to model that on the computer. You ready, my friend?
Yeah, dice vamos a tirar upstairs.
It's probably gonna be